Hello friends, my name is Manshu Bhardwaj and in this video I'm going to show you how to do grading and georeferencing of magnetic magnetic data. I have an aerial magnetic data and I'm going to show you how to do grading of this data on Python with some open source available packages and uh, uh, the georeferencing of the raster image because and also in this video I will show you how to apply various filters on the magnetic grids. So this operation generally done by various softwares like Oasis Montage and others, but you have to pay a very heavy price for purchasing those software. So those operation can also be done freely on Python. And in this video, I'm going to show you how to do all such operations without paying a penny. So I'm going to share my screen and you just follow the step uh, to process the magnetic grid data and first, and then I will show you the georeferencing of the raster image. So in this video I have already opened a Jupyter notebook. This Jupyter notebook you can download from the Anaconda website. Anaconda. Once you have installed the Anaconda on your system, you can have this Jupyter notebook, or you can separately install on your system. So this is a basic notebook that is very popular nowadays. So I need first some basic packages I think you will be aware of. First the NumPy and Pandas and the Matplotlib. But apart from that, you also require SciPy for interpolation because magnetic data grading are done through minimum curvature grading. So that can be done using SciPy packages. There is an interpolation function and grading of data options are there in the SciPy package. And also you also require raster IO. So raster IO you should also install on your system because for processing raster image you require that software. So before coding, I must show you the data. So I have this mag data 11 which is an aerial magnetic data. So this data contains x, y, and z coordinate and the magnetic value, which is the corrected value. Means after all corrections, this is the final magnetic anomaly that we get. Means first we have to do the diagonal and base station correction, and then the latitude correction, and all. After all such correction, you get this data. So in the separate video, I will show you how to do correction on raw magnetic field data. But in this video, I will only show you the grading and the filtering operations on magnetic data. So let us first load the packages. So I'm going to load the matplotlib.pyplot for um, uh, plotting the grid and all the images. Then I also required data frame. The pandas data frame is also required. Then you also required numpy and import a raster IO. This package I have already installed on my system. So you can Google the raster IO installation. You will get the pip installation or the conda uh, installation. Uh, so one package also required is SciPy. So from SciPy, you just uh, you just need interpolate scipy.interpolate interpolate import grid data. So this grid data. So these are the basic packages that you require for grading the magnetic. data. So let us process the system, then just load the data first. So I'm going to load the data CSV file in which my magnetic data is stored. So I'm going to read the CSV file first. So it is mag data 11. So mag data 11 dot CSV. So let us see the header first. So this is the my data set. So you have X, Y, and Z data set, and also you get the corresponding magnetic value. Now, first of all, I must clear the coordinate system is NAD 83 UTM 15 degree north. So you have to assign this coordinate reference system first. So before going to assigning the and georeferencing of the image, first let me show you the flight path. So I'm going to plot the flight path, which is nothing but the flight path. So select the quick size this and then plot the flight path POT dot plot. Okay, dt x and dt y. Let us plot the flight path. So this is the flight path along which the magnetic data has been acquired. So we have to create first grid. So first we need to prepare the mesh. So uh, first let us create a zip of my points. So zip and dt x comma dt y. Okay. So this will create a zip. Then you need values, corresponding values is the magnetic value. So dt dot mag dot values. So you first create this, then you get the minimum and maximum extent of x and y coordinate. So just get the minimum x coordinate, maximum x coordinate, and minimum y coordinate, and the maximum y coordinate. So you have got the extent. So now you have to do mesh the vertical and horizontal. You have to select the cell size first. So I am selecting the cell size. You can select so for vertical for y-axis I'm just dividing the entire extent into 1000 cells. So maximum minus minimum divided by 1000. Similarly for vertical for along y-axis max y minus min y divided by 1000. So this is the cell size along x and y axis. Now let us create a data point along x axis. So minimum x comma maximum x plus res1 comma res1 is the step size. Again, y range, you can set the y range also. Range minimum y comma maximum y plus res2 res2. So now you have ranges along x-axis and y-axis. Now what you need to prepare a mesh. So x comma grid x comma grid y. Let us using a np dot mesh grid np dot mesh grid. What is x range comma y range? Now you have grid. So let us see. So you can have a grid along x-axis. Similarly, you have y-axis. So you have prepared a x and y. You have prepared a mesh grid. Now you can do the gridding. So let us use the grid data of SciPy package to grid the magnetic. So I'm saying that the name grid mag. So it is grid data. Then you have to supply the points that we have created. Then you have to supply the values. Then grid x, grid y, grid x1. Yeah, you have to assign a method. Which method you are going to use for interpolation? So there are many methods, many options available, like linear. Then you can also use spline interpolation, but it is recommended that use minimum curvature. So minimum curvature fitting can be done using cubic method. So, gridding has been done. Now let us show the gridding first. So use plt.imshow function to show the grid. So grid mag, then say origin. What origin you will use? Lower. Okay. Let us see. This is your grid. But problem is that you can see the value is not what you have. Just look at the x and y coordinate. It is not the same as you have supplied. So you have to select the extent also. So extent, because this raster image, that this grid is not georeferenced. So you have to georeference first. So in order to show the coordinate, you have to use extent. So extent, you give the extent, which is nothing but min x comma max x. Then you have to give min y comma max y. So this is the extent. Now you plot, you will get the coordinate. So now you have the field coordinate also. But again, this image is not georeferenced. So in order to save a geotiff file or a georeference file, first you have to georeference this image. So I'm going to use the raster IO package that I have loaded earlier. So raster IO, from raster IO you transfer From raster IO transform, you import transform, sorry, fin function. So I'm going to raster IO transform import no module name raster this one, no module name raster IO transform. Transform. uh, So now it has been imported. So let us do the fin transformation first. So transform is equal to fin dot transform. So I'm going to do the fin transformation, means translation. Sorry, because this grid has the origin 0 0. So I am going to transform it to the min x and min y value. So so as you do so in so as you do so in a simple coordinate transformation, you translate the coordinate or you rotate the coordinate. So I'm just going to do the same thing. So 0 0, so grid 0 0 value will be my origin. So this 1 divided by 2, and this will be the origin of the uh, new coordinate, new translated coordinate. So grid 1 or grid y, it should be grid x, it will be grid y 0 0 minus s 2 divided by 2, and then also we have I'm going to scale also. Scaling is also required. So scaling should be in the ratio of vertical. I'm going to maintain the scale of the data. That is why I'm doing the same ratio. Now translation. Translation. This should be translation. So now the coordinate system has been translated to a new origin. You can see the origin is now 32 so 3,29,995.5 and 66,29,193.1. So the coordinate system has been translated. The image coordinate system, the origin of the image now has been translated. Now another thing, you have to assign the coordinate reference system. So this is a NAD83 system. I'm going to write this dataset is NAD83 UTM 15 north coordinate projected coordinate system. So for this you just get the EPSG code. So EPSG code you will find by googling, or you will find the ISRI map also. So for NAD83 EPSG code is I'm going to assign a variable raster CRS to get the coordinate reference system from CRS. So first you need to import the coordinate reference system. So from raster IO you need to dots. There are various coordinate reference system is available in raster IO package. So you just import CRS. Once you have imported the CRS from EPSG, so for NAD 83 UTM 15° north, you have the EPSG code is 26,000, sorry, 915. So you get the raster coordinate system. So you have to assign this to my raster image. So you can see the what you have, whether you have got. So you can see the EPSG is 26,915. So this you have to assign because this is corresponding to NAD 83 UTM 15 north. So now you have to assign these transformation and the coordinate reference system to our grid raster that we have recently created. So let us name a variable in which you have to store the raster parameters. So raster.open. You just name the file in which you want to store this raster image, this georeference raster image. So I'm going to name it aero mag dot tip. So I'm going to store this file into this with this name, and I'm going to write. So I'm going to give the flag of write. Then driver I'm using what, geotip. So g tip driver I'm going to use. Then you have to give the data type. Data type is what? Data type is nothing but the grid map, or what data type we are using? Grid map, in which we have created the, we did the interpolation using. So grid map dot d type is the data type. Then count one. How many images? We count one. Then you have to get the width of the image or the raster file. So width is nothing but the same grid mag dot shape 0. Then height HIEDST height height is you get the grid mag dot shape 1. Then you have to get the coordinate reference system. So we have just used the parameters of coordinate reference system into raster CRS. Then transformation. Just transform. So we have already created the affine transformation. So you just assign transform. Okay. So now I have assigned all the parameters into this new file in which I am going to store the my raster image. So let us write the raster file. So raster file, no, sorry, not raster file, but grid map. Yeah. So raster file dot write. You have to grid map is the interpolated variable for interpolated grid data that we have created here. I'm just assigning here grid map, and then indexes you just write one. Then you have to close the raster file. Once you have assigned the value, you have to close also. So I'm going to just close this. The raster file is not there, one spelling mistake raster. So now you can see that the arrow grid has been saved with proper georeference coordinate system. So you can see the actually this is not opening up. So a georeference grid name arrow has been created. Sorry, you have to create once again. So this tip file contains the georeference raster image that we have created. Now let me show whether it is not showing here, but I'm just going to plot. So now, and once we have created a raster image, now I'm going to use a package called interface, and I will show you how my grid looks like. So you just import interface. You have to install it. This is again a open source software. So you just install it, and it's taking too much time to load because my system is already. So I'm just giving a file in file, or I'm just going to get the name that we have created, arrow mag dot tip. So I'm going to load this. Uh, so grid 1 is equal to uh, interface dot open. So this will open your grid file. So now my grid file has been loaded. Now I'm going to show you the loaded grid file. So grid1 dot show. This function will plot your grid data or raster file that we have already created. So it's taking time to load because my system is slow. So it's taking too much time. Not good. So this is the grid file that we have recently created. So you can see how the color dynamics is good, but you can set the color dynamics using a keyword called uh, you can use a keyword called map norm. You can set the norm of the image. So grid1 dot show then so cmap norm is equal to equalize. So you can use the histogram equalization to correct the image. So cb so histogram equalization you just use. So you can set the dynamic range, or you can equalize the histogram of the color map by using the keyword equalize. Cmap now. Just wait. Now you can see the dynamic range has been reset. But already, so you have created the grid. You can see the coordinate that you have set, the vertical, the y-axis coordinate, all has been set. Now, what I need, I have created now for filtering operations. So we have created a grid and a magnetic grid, 2D grid of magnetic anomaly. You can see this is the high value and the blue one is the low value. Now, if you want to clip the data, Now we are going to do various operation, filtering operation like horizontal filter, horizontal derivative, then derivative along y-axis, then vertical derivative, or pseudo gravity filtering, or many kind of filtering. We can do this on Python also. So for that you have to prepare functions and you have to write function. I have already written the function. So I have already written functions in various uh, Python files. So for example, this is the function I have written on it. So you can write these function. If you have the formula, you can use you can write functions. So I'm not going to give you how to write function because it will take too much time, but I have attached I have just given a link of my GitHub account from where you can get the code. So first of all, let us and see how simple it is on Python. No need to. So let us first clip the data. Means if you are interested in certain zone, so we can clip also. So let us clip the data first, and then go for filtering operations. So I have created a package that I am going to load here. So already raster I use, so I have written from grid import this grid package I have prepared for my magnetic for applying various filtering operations and all. So let us import this package and let us create a function also, definition function. So I'm going to create a function fopen and then input file, and I have already, no need to type, I have already created this function here. Just typing is taking too much time. So type here, we just we have created this function for opening up a file. So nothing, I have used a similar code that I used here. Raster file open. So raster IO open. So you can open the raster file. CRS is none. I'm not going to assign any value CRS, but you can assign the value. You can get the CRS value now. So this function I have created. Now just open the function. So grade11 is equal to f open, give the name of the raster file. What is the name of raster file? Arrowmap.if. Also you can assign the coordinate reference system. So coordinate reference system is what? Raster CRS. So raster CRS. So I'm going to assign this coordinate reference system. You can also give the name, but no need to give the name. So now my grid has been uploaded, arrowmap.tip. So just show the grid. So you can see the same grid has been uploaded. Now I'm going to clip the data. So I'm interested in this part of the zone. So I'm just going to give the extent of the zone. So just clip the data set. So let us create another grid or subgrid. So grid 2 and grid 11 dot clip. I'm going to clip a certain part of it. So x min value have to write. So I'm going to give the x min value 335 5000 X max value is 338,000. Then y min value I'm going to give it to 66380030, and y max value is 663430. So now I have clipped the data set. Let us show the clipped grid. So you can see the clipped grid. So this is the clipped part. Means I have only focusing on this part of the area. So now let us apply various filters that I have created. You will get all the code on the link given below on my video. So just visit my uh, GitHub profile, and from there you can download all the codes for filtering operations. So let us do the upward continuation. So as you know, upward continuation uh, upward continuation highlights your highlight the regional the uh, the signal coming from the deep interior of the earth. So let me do first. Where is my video? Okay. Yeah. So now, so first let me explain what so I'm going to apply the upward continuation. So what upward continuation does? It just highlight the signal. It just the amplify the signal coming from the deep interior of the earth, whereas it suppresses the signal of the shallower origin. So let us do the upward continuation first. So for upward continuation, you just give you have to give the height first. So let us do the upward continuation of this grid 2 dot up. Okay. So z is equal to I'm going to give the 200-meter height, or 2000 1000-meter height, let us say, and also give the hillside zf value. This is say 1000. So this will do the upward continuation. So let us see. So this you can see that the upward continuation of the wave. So for this entire data set, we can also do the upward continuation. So ax1 is equal to grid 1 1. This is the larger grid. Up, you can do the upward continuation for this also. So grid 1 1 dot up. Uh, z is equal to, let us say, 1000 meter, and uh, so dot show z up, say hillside is 1000 meter. ZF is 1000 meter. So see the upward continuation for the entire grid, the larger grid that I have created. That is good. So for larger grid, it is taking too much time. Actually, it should not take this much of time, but because my C drive is full, that is why processing is taking too long. But it might run very faster on your system. Let's see. This is the upward continuation of the entire uh, grid at the height of 1000 meter. Now let us do some derivative. Let us apply some derivative filter. So I'm going to apply the smaller grid data, the derivative filter. So ax is equal to grid grid 2 dot dx for derivative along x-axis. So dx dot, so let us give the hillside value of 1000. So this is the horizontal derivative along x-axis. Now for horizontal derivative along y-axis, you have to give the function name dy dot show. So for dx dy, all code I have given. So this is the horizontal derivative. Resolution is not good because you can also improve the resolution by having a more densely populated data. So this is the horizontal derivative along y-axis. Now let us take the vertical derivative. This is the horizontal derivative along y-axis. Now let us take the vertical derivative. So dz dot show zf is equal to 1000. So this is the vertical derivative that I'm going to calculate. Now I can also apply the tilt derivative. So what tilt derivative? It gives the peak highest value at the peak of the anomaly. So I need to type just tilt to give the tilt derivative. So let us say tilt. So let us say give the calculate the tilt derivative of the entire grid, the larger grid. So you just need to type tilt and then dot show. So zf is equal to 1000, and you can calculate the tilt derivative of the magnetic anomaly. For a smaller grid, let us for a smaller grid, you can also calculate the grid tilt derivative. Zf is equal to 1000. For larger one, it is taking too much time. Let's wait. It's taking too long. Process zero. So the tilt derivative has been calculated. So this is the tilt derivative. Similarly, for smaller grid or the cleft grid, you can calculate the tilt derivative. Let's see what happens. This is the tilt derivative of the cleft grid. Okay. So this is all about the various filters. There are many more filters like pseudo gravity filters. So let us apply the pseudo gravity filter also. So for pseudo gravity filters, or let us calculate the horizontal gradient filter. So for horizontal gradient filter, I'm going to apply it on the smaller grid because larger grid is taking. So horizontal gradient magnetic filter I'm going to apply, and so whether you can adjust the hillside value by assigning a number here. So for horizontal gradient magnitude, let us see. This is the horizontal gradient magnitude filter. So these are the various kind of filter options available. There are many more filter options I have created, like reduced dipole, or the pseudo gravity filter. So all the codes are available on my GitHub link. You just go and visit my GitHub account and download the code. So the so this is all about the various filtering operations that can be applied on Python without using any software or any uh, without paying a penny, without paying a single penny, or without paying money. You can use these filters. You can generate grid on Python and use these filters. So this is all about creating grid, geo-referencing of the image, the raster file, and the application of various filters on the magnetic data. Now, in the subsequent videos, I'm going to do the 3D inversion of the magnetic data. So you will be getting the subsurface parameter or the susceptibility distribution corresponding to the magnetic anomaly. So I will be using the same ferromagnetic data uh, for magnetic inversion. So I will apply various inversion techniques and create a 3D model of the subsurface. So just keep on visiting on my channel and view how we can do the inversion on Python without using any software. Just code on Python and get the result. So thank you very much. So this was all about various filtering operations. Thank you very much for viewing my channel. Now in the next video I will show you the basic corrections that we apply on gravity or magnetic data on Python without using any software or any package that you have to pay for. So I will create various functions for various correction like terrain correction, latitude correction on gravity data, or the uh, drift instrument drift correction, then various other correction like free air anomaly, free air correction or Bouguer plate correction. So these in the subsequent video I will going to show you uh, I'm going to show you how to do the corrections on gravity data as well as the magnetic data. So magnetic data you require only diurnal and the latitude correction, but for gravity you apply various corrections. So let us wait for my other video. Thank you for watching my channel. Goodbye.